Oh yeah, welcome to the stream. Back at another one at a couple different days simultaneously of our various projects. One is mandatory, the other is willingly, but it's still it's highly determined, high determination for it, for the conclusion of the project to finish it. You know what I mean? So that'll come in due time. In due time. But we're kicking it off. We're gonna do some electrical analysis to begin with, and then I'll get into the build later. But I don't want to build right now. Let me check the quality of the stream. Live right now. All right, that sounds good. My phone needs a charge too. All right, that sounds good. My phone needs a charge too. Yeah, very well. All right, getting on with it, doing some phase and shit, some phases and shit. All right, I did already kind of get going, but we're gonna start from the beginning. Got a nice white blank piece of paper. Let's roll on down into it now. Alright. We'll get the focus up. It'll go. Trust. Alright, so we have this handy dandy independent current source. Now this pathway is going to trickle on down here to this resistor. And this resistor is going to come to a pointer right here of a positive probe. Right? That's where we're going to probe the positive input to our exterior circuit. You know what I mean? Because we got to plug something into it, right? So we have this resistor here, that's 12 ohm. Right, we have this inductor here, call that good, 25 microhenry. Alright, we have a resistor, that's 20 ohm, and 125 nanofarad capacitor. 25 nano. Alright, and then this is labeled IG, and then we have a current magnitude and a wave function. We essentially have a wave function, a sinusoidal function. So IG equals our source, a sinusoidal source, 5 IG equals 5 cosine 800,000 T amps. I don't like the way that I wrote that cosine. Let's run it back. That's a little bit better. It still looks a little odd though, right? Can you read that? Yeah, fair enough. Alright. Oh man. Yeah, that's the way that'll be. Alright. So we have IG. I want to use a current dividing network, current dividing formula. So I essentially want to put all of these impedances in parallel. As we can see here, there's a series network, but I can still find the current running through just this branch of the parallel network. So that would look like so we want to figure R total, rather Z total. Let's label it correctly. Z total, equals 125 nanofarads in parallel with 20 ohm in parallel with 12 plus J omega L. Right, and that's that equation consisting of, well then this is incorrect too. Yeah, this would be negative 1 divided by 125 e to the negative 9. Alright, that's J, that'd be negative J all multiplied by omega, so let me just write it out. Omega C, right, in parallel with 20 ohm in parallel with j omega L. Okay, that's the whole thing. So omega c, let's calculate that first. -1 divided by 8e to the 5 times 125 e to the -9. Right, okay, so -10. 10 in parallel with, well, -10j. In parallel with 20, 20, yeah, that's it. 20 in parallel with j omega L, 8e5, right, and that is it to the 5th, 1, 2, 3, 4, 5, okay, 8e5 multiplied by 25 microhenry times 25 e to the -6, 20. Right, okay, so now we're gonna add these. Rather, it's gonna be, so 1, okay, and then that again to the -1. Okay, that's the result. Z total. So that's our Z total. Right, yeah, okay. And then Zn equals, well, it's just going to be this branch. So 12 plus 20j. Yeah, that's it. Okay. And then now the current divider equation is Ig multiplied by Z total divided by Zn. In order to do division, I'm pretty sure we have to put it in polar form. I believe so. So we'll go ahead and do that. Let's go to polar form. That's gonna look like, and it's just like simple or similar to vector arithmetic. You know, we're looking at the square root of 7.84 squared plus 6.88 squared, and then the phase would be the inverse tangent of 6.88, well, negative 6.88 divided by 7.84, okay, degrees. it this way. Equals magnitude 10.43, phase angle, inverse tangent, negative 6.88 divided by 7.84. Okay, we have an angle of negative 41.3 degrees. Okay, now let's solve for Zn. Square root of 12 squared, 144 plus 20 squared. No. Sorry, I had a brain fart. Inverse tangent, negative 1. 20 divided by 12 equals degrees. Oh, my lead's breaking, it's separating from the pencil. Magnitude 23.3. Oh, 2. Angle, inverse tangent 20 divided by 12. Whoops. 59.0 degrees. Okay. So now if we go ahead and divide these, let's see, we got 10.43 divided by 23.32, we get 0.44. So, alright, we'll write it all out. 10 point, so IG equals, now we'll write him here. 10.43. Bro, the lead's breaking. Are you kidding me? Oh, now, so there it goes. See that? Alright, 10.43 divided by 23.32. Oh yeah, angle negative 41.3. Angle 59.0 degrees equals 0.44, 7 angle, and then now this is now the phasor we're going to do a subtraction. Okay, we don't do a division. So 41.3. Oh wait, negative 41.3 minus 59 degrees. Negative 100.3 degrees. And now that's just IG. So it's 447 milliamps. Okay, phase angle of negative 100.3 degrees. Okay. And that's through this branch. Wait, IG? Wait, that's just the impedances. I haven't multiplied IG yet. And IG would just equal, let's write IG in phase form, equals 5 angle 0 degrees. Pretty sure, yeah. So if we multiplied it, we would have no addition, but we just have 0.447 multiplied by 5. So IG equals 2.24 phase angle 100.3 degrees amps. Alright, there it is. Hopefully that's it. So that would be the current in this branch right here, and both of these series elements share the same current. So to get the voltage, we should be able to multiply this current, IG. We shouldn't call this IG. Well, no, that is IG. Oh, wait, no, that was a multiplication by IG. So now we took that. And then we'll call it IL. IL equals 2.24 phase, negative 100.3 degrees. Okay, so now this, now let's consider ZL equals J omega, which is 8E5, multiplied by L 25E to the negative 6 equals 8E to the 5 times 25E to the negative 6 20. Oh, right. We already calculated that. 20. Okay. And now with this carries a positive 90-degree angle, does it not? But then that wouldn't be 20J. That would just be 20. Wait, so 20J in the case of, how would that work? 20J. For 0 plus 20J. Square root of 20 squared would be 20. So 20 angle. How does that affect the angle? Oh, inverse tangent. Yeah, but the completely imaginary. So what's the logic to that then? I really don't know how to derive that. But this must be positive 90 degrees. But especially if we're looking at terms of current, it's the current which lags. So would it not be a negative 90? Let's just take a look. So if I were to take 20 times 2.24, I get 44.8. And that's, let's see what our negative 100.3 plus 90 is negative 10.3. Yeah, that's totally it. Okay, so it is an addition of 90. I was considering the perspective of the current, and the current through an inductor lags, right? It initially acts as an open circuit and over a long time begins to look like a short circuit. So the current initially lags, but we still consider it to be a positive 90-degree phase shift, right? Because if we were to model it in the complex plane, graphically, then it would point upward, right? The inductor impedance and the capacitor impedance would point downwards and be negative. You're welcome. Yeah, there you go. There it is. All right, so 90 degrees. And if we were to take IL multiplied by ZL, we would get 2.24 phase negative 100.3 multiplied by 20 phase 90 degrees equals 44.8 angle negative 10.3. Volts. Yes, okay. By how many nanoseconds does V naught lag IG? How many nanoseconds? So V naught lag IG. So if we were to convert this back into time dependent form, it would simply look like 44.8 cosine omega, which is 8E5 AE5T minus 10.3 degrees. And then we want to essentially subtract which one? Does V naught lag IG? V out lag IG, and then IG would be some. Does it lag? Surely that'd be a subtraction, no? Right, that'd be a subtraction. Minus 5 cosine AE5T minus 0. So I did the phase angle divided by omega, so that'd be negative 10.3 divided by 8 e 5t delta t. The change in time would equal negative 1.28 8 e negative 5 equals, and it says in what? How many nanoseconds? Well, that's not all right. Shit, I don't know how to solve for that. But how many nanoseconds does V naught lag? V out lag IG? Alright, fine. Yeah, let me look this one up. So delta T equals theta radians. Oh, that's literally why, because I didn't have it in radians. I had it in degrees. So, okay. Phase in radians. No, we don't need any of that. So it's going to look like phase in radians, and then our phase in radians is, so we have negative 10.3, negative 10.3 pi divided by. Okay. Okay. It lags. Yeah, that's the whole purpose of it, right? So, radians. Wait, phase. Okay. So that's that's the in radian, yeah. That's delta T in radians, right? So we needed radians and then we had radians, which is 800,000 AE5. So we take 0.1798 divided by AE5 equals radians. Equals 2.247 e to the negative 7 equals 224.7 nanoseconds. Okay, so that's how many seconds that V out lags IG by. Alright, this is our input, and then this is what we're proctoring with our probes. Yep, and that is the correct theorized value of delta T, the amount of time that IG lags, the amount of time that V out lags IG. Alright, moving on. There's 11 pages. Whew, that's crazy. Oh, okay. Alright. Well, we should jump to that now. I guess we could. Alright, now we're back to this. Alright, let's get into it. Fuck. I don't know what's going on here. A whole lot of tomfoolery, monkey business. But we have a lot more that we need to build. And so I guess let's build it. I think I need to convert this into something different. I'm not really liking this because I think this needs to be on the exterior of this, but is it going to be as rigid? You know, so that is the question to ask. Perhaps that would be more support and ideal. How large would that wheel be? That'd still be fairly large. Okay, let's do this. So I need 2 measurements. Okay, come back here. So I need 2 measurements. Let's look from the very top. Looking from the top view. Okay, right. That's awful. That's better. That's alright. There you go. Something like that. Alright, whatever. Okay, and I need this dimension here. We're gonna take note, write it down. What else would I need? Something from here, not necessarily. That's pretty much it. Well, that, I guess. This to here, center to center. That's gonna be that. And then doesn't diameter look something like that? Like something like that, right? So what is the diameter of that? We also need to check this. So assembly, can I do a measurement? Insert. Move component. Yeah, let's transition back. Let's see. Evaluate. Evaluate. measure. Let's try that. 12 inches. Okay, 12. Okay, 12. What? Why'd that happen? Okay. Let's not do that. Let's try again. Measure. So, wait, what was I trying to measure? That distance. This. And like that point. What the fuck is that? Well, that's really interesting. I don't think I want to do that anymore. I guess what, we just have to go to the file of this guy. So let's go to this one. Alright, let's open this up. This is dog boy. And then we can do some smart dimensions. Yes, smart dimension that hoe. Let's do this guy. What's happening right now? What the? Come on. .35. I just need it. 6.35. But that's not like an actual height. Why can't I get a height? I guess that would work. Let me try this. So. What the? There's no way. How? How is that the result? I guess I can use it 6.35. I mean, we can figure that out then. That's probably fine, just like a 5-inch wheel. I don't know, maybe 6-inch. We'll see. Okay, now what's the I need to know the diameter of this. So let's look from the right side. I need the diameter of this. Come on, buddy. Give me some. Okay, maybe I need to exit the sketch. No. .75. I could probably just, yeah. 0.75. Alright. Is that all that I needed? I believe so. Yeah, I believe that's all I needed. So let's go ahead and start a new file. Do part. Okay. Start from the right side. I need to see all of the planes looking from the right side. I'll just do that right here. Front plane, right side, right plane. Yeah, that's where we need to start, right? Okay, let's do it. Features, extrude boss base, right plane. We're gonna create a circle at the center. How large should our wheel be? In diameter, let's do 6. Oh wait, first check it. Oh fuck, what happened? Alright, let's try that again. Good. Smart dimension. No, we make it 6. Okay, check. Yeah, we'll do some more. The rim, approximately, let's see, check, smart dimension. 3.14. That's kind of cool. I didn't even mean to do that. Let's make it pi. Why not? And then we have maybe this isn't necessary right now though. Yeah. Alright, let's just do this for now. 12 inches, so 6 is even small. I may need to put 2 wheels together to really achieve what I desire. I want it to be a wide wheel, but that's half. I mean, we could just do it then. So let's do 2 4-inch wheels. Okay, we'll duplicate that. Yes. Let me model 1 first, and then we'll do it. We'll duplicate it. Now is that literally just the center? Yeah, it would be. So 0.75, right? Wait, 1.5, and then we have the bearings inside of there, right? 0.75 size, inside diameter. Okay, I think that'll do. Okay. That was good. Well, actually, wait, no, that's not. What the fuck? He just keeps adding to one side. Bro. What? Wait, so when I go in direction 2, okay. Wait a second. So is this also facing the same direction? Okay, that just adds to that side. And that adds to that side, but it's moving everything. Fuck. This is bogus. Shit, okay. I bet I could easily find a model. Yeah, why not just do that? It'd be so much better. Okay, one moment. Let me attempt to find a model. It'd be so much easier. Alright, I'm also going to